Our next lecture is going to be on the central limit theorem. The central limit theorem in Brace's 10th edition is 6.5, but you will find it in my notes in section 7.2. So what we have here is the central limit theorem stated quite simply, and this says basically that if x is a random variable from any distribution, now that's really important, it's any distribution. So let me write that in great big capital letters. Any distribution. And it has the mean of mu and the standard deviation of sigma, whatever they happen to be, and we have n samples drawn. Now this is our connection to sampling distributions. Then we know that the means of these samples, right, these x bars, the means of the samples, those are distributed normally with a mean that is equal to mu and a standard deviation that is equal to the original standard deviation of the population divided by the square root of n. Now this sigma divided by the square root of n, this sometimes is abbreviated by books as sigma sub x bar, and it is also known by the name of standard error. So those are some things that you need to know about this sigma divided by the square root of n so that you might be able to locate it more easily. So this is the standard error, and that's what you see here in the central limit theorem. And this mu is sometimes also referred to as mu sub x bar. But because mu sub x bar is equivalent to mu, then there's no difference there whatsoever. So that is what the central limit theorem says, and that relies on the theory from the sampling distributions. So what we're going to look at here is the difference between what we talked about in section 6.3 and what we're talking about in this section. And before we can apply the central limit theorem, I really should note to you right here, this little note, is that in order to apply the central limit theorem, your sample size has to be greater than or equal to 30. Or if you know already that it's approximately normally distributed, then you can apply the central limit theorem. But if you do not have either of those two requirements met, the central limit theorem should not be applied. Now this approximately normally distributed, this can be shown or proven using the techniques that are mentioned in my notes in section 7.1's ending up here. Is it section 7.1? No, it was not. It was at the end of section, at the end of chapter 6. So at the conclusion of chapter 6.3, where it was talking about if something is approximately normal or not. So if you wanted to take a look at this more thoroughly, you may want to take a look at page 14 of section 6.3 notes. So chapter 6 notes from Brace, and that's page 14. So this is how we could prove that something was approximately normally distributed. So now back to our original task here, which was talking about our differences between what we had in section 6.3 and what we're going to be talking about now. In section 6.3 we had discussed distributions where we had a single random variable being observed. Now we're going to be taking a sample and we're going to be talking about its sample mean. So a soft drink vending machine is set so that the amount of drink dispensed is a random variable with a mean of 200 milliliters and a standard deviation of 15 milliliters. So in other words, X is normally distributed with a mean of 200 and a standard deviation of 15. And because it's normally distributed, this is satisfied, and we know we can apply the central limit theorem. Now question A says that I want to know the probability that this random variable is at least, so the smallest it is, right, greater than or equal to 204 milliliters. So that means I walk in as a single customer and I want to know what's the probability that I get 204 milliliters of soda. Well, every single one of us who walk in, the probability of getting 204 milliliters is, it's over the mean, right? So I know it's going to be less than half, but it's fairly close to the mean in terms of the standard deviation. So I know it's a pretty good chance that I'm going to get the 204 or more, but it's not a huge probability. So it's less than half certainly, but it's not broaching up there on really close to half. So we are going to look at how we would find this. Well, this is section 3 all over again, right? 6.3. I take the x, I minus its mean, and I divide by its standard deviation because it's a single observation from a normally distributed population. So 204 minus its mean 200 and divided by its standard deviation 15. So this gives me the probability that my x, or excuse me, my z is greater than or equal to, and we have 4 divided by 15. So 4 divided by 15. And that, oops, I don't know if that was right. 4 divided by 15. Yeah, 0.26666. So this gives us 0.27. And now if we were looking this up in a table, obviously what we would do is we would go over to our table, so let's go find it, and we would look up 0.2 here, and then 0.7 over here, and it would be 0.3936. So 0.3936. And I know that I can look it up in my z, negative z, right? Because here's my 0 and here's my 0.27. And this 0.27, I want to be larger than this. This is a tail value, which is the same as a tail value over here, which is what I just looked up. So here we have my 0.2s and my 0.7s over here, and we see 3936, and that's the probability. So that would be the probability of getting 0.27 or larger, whereas 204 milliliters or larger. Now my next example says the average amount dispensed in a random sample of 36 is at least 204 milliliters. Now this is an application of the essential limit theorem because I'm saying that x bar is greater than or equal to 204. So now it's not in one single, but my observation in 36. So that's like a whole class going in and getting sodas and seeing if the average is. Now this probability is going to be less than the probability of one single one because all of them should be close to the 200, right? So it should get closer and closer to 204, and therefore we're going to have less probability that it's 204 or further away when it's an average. So 204 minus the 200, because that's still its mean under the central limit theorem, divided by the 15, and then divided by the square root of 36. Now I want to point something out here. One of the things that I want to point out is the fact that this 15 divided by the square root of 36, in the denominator, this 36, the square root of 36, it ends up multiplying by the whole thing. Another way to write 204 204 minus 200 divided by that radical is to write this, and then that being multiplied by the square root of 36. So the value that we got before, the 0.27, that one actually gets multiplied by 6. So this is actually looking at a value that's about 1.3. So if this is 0, our first one we were looking at 0.27, right? Well, this time around, we're going to be 6 times larger than that. And our value is going to be way out here at approximately 1.3. So that's going to be the change. So what you see here is as that sample size increased and the jitter decreased, right, the value decreased or the average decreased and got closer and closer to the actual mean, then as that happened, it's less and less likely, as we see here, right? This is a lot less likely to happen out here than the black one here. This is a lot less likely to happen. So now what we have is the probability of a z being greater than or equal to, and I can go to my calculator. I still have the 0.26666 there, and I can just multiply that by 6, and I get the value that I wanted. Now, obviously that was a lot bigger than I thought it was, because I had a lot of round off the error there, right? 0.3 times 6. No, it's 0.18 was what I should have said, huh? So here we go, 0.6000, so 0.60. And so now let's go ahead and take a look over at my table again. And I have 1.6, so 1.6 right there. And 0.0, of course, is that one. And so the probability this time around is 0.0548. So 0.0548. And you see the probability this time, sure a heck of a lot less than the probability of one of us walking in and getting that soda that's 204 milliliters. And that's because in the central limit theorem, what we're observing is that the jitter gets smaller and smaller around the actual average. So that's the central limit theorem being applied. All right, now let's take a look at our next example here. And why don't you guys see if you can do this one on your own, and I'll come back in the next video and do it. So a random sample of size 64 is taken from a normal population with a mean of 51.5 and a standard deviation of 6.8. What's the probability that the sample mean will exceed 52.9, fall between 50.5 and 52.3, be less than 50.6, and what's the probability that a single observation would be below 50.6? So see if you can take care of that one on your own. The next video I'll do that problem, and we'll look at the next one as well and talk about calculators following that.